Hey guys, Quiff the Lazy Geek here, and today we're going to talk about using camera lenses for astrophotography. And by that I mean not just standard kind of like Milky Way type of photography, but really going deep inside nebulae and star clusters and galaxies using camera lenses, maybe with a DSLR or maybe even like I have here with a dedicated cooled astrophotography camera. And so I will talk about what criteria to look at when you're choosing a lens for astrophotography, and also how you can pair it with a camera, how you can control it, how you can focus it, and how you can get the best possible image quality out of your lens for your particular setup. And all of those are actually fairly complex. Now I'm going to start by introducing what is generally recommended for beginners in astrophotography, and by that I mean really about like people who want to go after galaxies and nebulae rather than the whole Milky Way, as a general kind of wide field type of thing. The recommendation is typically to go for an actual telescope, typically called a refracting telescope or refractor or a frac sometimes. And refracting telescopes are basically the same as camera lenses, except that their only purpose is to be super sharp at infinity focus, meaning when it's focusing on very far away objects like stars are. And because of that, those refracting telescopes will have excellent image quality typically, and but there is a drawback. They're fairly big, they're fairly heavy, and they're fairly slow compared to lenses in terms of focal ratio. So let's look at one of those. And here is a very small, by astrophotography standards, this is one of the smallest refractors you can get for astrophotography, and that thing is quite heavy, actually, much heavier than a lens. It is f4.5, so which is actually one of the fastest refractors you can get for astrophotography at a reasonable price. And it is quite large, quite heavy, and if you want to do focusing, you'll need to either focus manually using this focus knob or fit an autofocuser on it. And it gets quite involved. Now this thing still has 275mm focal length along with a reducer that I have here, so it is not bad at all, but you can see it is much more unwieldy than using this 200mm f2.8 lens, right? So this is one of the main things about lenses, is that they are smaller, lighter, easier to just like take with you immediately for astrophotography versus this kind of big thing, which is actually super small by astrophotography standards. Those refractors can get very big very quickly, especially like when you increase the focal length. So if that's the case, why doesn't everybody just use camera lenses for astrophotography? Wouldn't that be easier? Because they're lighter, smaller, faster. In theory, yes. The problem is that astrophotography really is a difficult topic, and lenses like this one, they're made really for everyday objects. They're made not for star fields. Star fields are basically the most challenging subject for a camera lens because the sources of light, they're pinpoints, and translating a pinpoint into a pinpoint for a lens like this is actually super difficult. And this is where you must remember one key thing with lenses is that when they are faced with the most difficult subject possible, like a star field, different lenses, even of the same brand, make, and model, will have different reactions. So you have quite a bit of variation between the same lens. So if I were to buy a second 200mm f2.8 Canon lens, Mark I for this one, I would likely get very different results, or somewhat different results on star fields than this particular lens does. There is variability, and this is not taken into account by manufacturers because they do not target star fields to have best possible image quality. And to give you an idea, I'm going to put on the screen now a sample that I had from a lens that I bought a few years ago called the Kowa Prominer lens. It came with a reducer that made it into I think 350mm f4 lens. And it has a sterling reputation. It's a fluorite lens. It's supposed to be extremely sharp, and yet, as you can see, the stars are not pinpoint at all. They kind of like have a a haircut there. It was super weird, and that was my first sample. And fortunately, I had bought that lens from an astrophotography shop, so I was able to complain to them. They got a replacement, and then the star shapes were very decent. They were not perfect, but very decent. And this is because these lenses, however sharp they are not made for astrophotography. So this is something to keep in mind. Now, we have ways to remedy that kind of stuff to some extent, although it is not perfect. And I'll go into those methods in a few moments. So also, when you are choosing a lens, besides variability that you need to be prepared for. So it is quite difficult to buy a lens and know for sure that you'll get good results. But one way to be sure that you will get better results is by choosing lenses that are not zoom lenses. Zoom lenses, they're made to have a lens that will move within your camera lens, and in addition to the focusing mechanism. And that means that they try to be sharp across a wide range of focal length. And that can backfire because they might be less sharp at some focal lengths than others. And they are usually less sharp than a prime lens, or a lens that has a single focal length like this one. And all of the lenses that I own are prime lenses. They're not zoom lenses, and I use them exclusively for astrophotography. So I have this one, Canon 200mm f2.8. I have this one, which is a Canon 135mm f2. I have those two, which are respectively, they're both 50mm. This one is f1.4. This one is the Plastic Fantastic at f1.8. And surprisingly enough, I do not own a Canon DSLR. I only use those lenses for astrophotography using astrophotography dedicated cameras. So that is the big recommendation. Buying a prime lens, typically they will have less variability than zoom lenses, and they typically have better sharpness on difficult objects like star fields than zoom lenses. It's not always the case. I have heard, although I have not confirmed, and I do not know whether it was checked on multiple samples or just one particularly good sample, who knows, that the latest version of the Canon 70 to 200mm f2.8 lens, Mark III, is actually super sharp at 200mm, and I've heard it's actually sharper than the prime lens at 200mm. How true is that on a star field? I do not know. So you want to check how good the lenses are for astrophotography. There's actually a good website for that, and I'll put a link in the description below, although it's getting a bit old, so it doesn't have like the newest lenses. Of course, when you're choosing your prime lens, you want to make sure that you get the proper focal length for your particular camera, whether it's a DSLR camera or a dedicated astrophotography camera, compared to the objects that you want to image. And for that, you want to compute your field of view. Now, once you know the focal length of your lens, you can go into a site called Astronomy Tools. I will put a link in the description down below. You can put in your lens, you can put in its focal length, and you can put in the camera sensor size and pixel size and that kind of stuff to get an idea of the field of view that you will have versus different astronomical targets that you may want to have. So that's a very important thing. Know what you want to image with your camera lens to choose the right lens for you. Now, in general, a very good compromise is the 200mm f2.8 lens for Canon. I think Nikon has a 180mm equivalent, something like that. They're very decent in terms of field of view. They'll give you good results with most astrophotography camera sensor sizes. Okay, now that we have chosen a lens, or that you know what to look for in a lens, you want to make sure that you have a camera that is paired with it. Now, the simplest thing is to just use a DSLR camera. So if you bought a Canon lens and you have a Canon DSLR body, just use that. And what's very cool with those Canon DSLR bodies or Nikon or whatever is that typically you can control them via an intervalometer, or you can connect a computer to them and control them via computer. You can even control the focus ring of the lens via the camera through a computer connection. Depending on your camera manufacturer, this is something you need to check. It is actually super useful because focusing a lens is actually super difficult and much more difficult than a refracting telescope. You can also pair your lenses with a dedicated astrophotography camera like I have here. And for those, you will need an adapter to that camera. You will need to respect the back focus of the lens, which is the distance between the lens and the camera sensor. For Canon, it is 44mm. If you are longer than that, by a couple of millimeters, you will not be able to reach focus on stars. So it does make things a bit more complicated, but dedicated astro cameras, typically you have cooling, or you have you can have a monochrome sensor with a filter wheel that will contain RGB filters, and there are lots of advantages to that. I won't go into the details in this video. Let me know down in the comments if you want me to go into more details. I'll also be linking above a video about astro cameras and how to choose an astro camera in general. With this particular astro camera, I have actually paired it with a Canon adapter that's called the Astro Mechanics adapter that lets me, that has a USB port on it and actually lets me control the aperture and the focus ring of my Canon lens directly, which is why I am using Canon lenses exclusively, because only I haven't heard of similar adapters at the same price range for non-Canon lenses. This is not because I love Canon in particular, it's just because Canon lenses have this adapter that can control their focus ring. And I'll get back to focus in a moment because focus is really hard. Now, if you're using a DSLR with your lens for astrophotography, there is one critical thing to know about DSLRs is that they have a filter above the sensor that is designed to basically take pictures in a very natural light to the human eye. But there are a lot of objects that you want to take photographs of, like the Orion Nebula is one, that emit at a specific frequency that is called H-alpha, that we humans are very insensitive to. And as such, DSLR cameras are also purposefully insensitive to using that filter. And that means that typically it cuts off around 75% of that signal, but it is very important for us as photographers to get more of that. So you have some very specific cameras that are made for astrophotography, like the Canon 60D-A or the EOS R-A, and A I think stands for astrophotography, I guess, that have a different filters on top of their sensor to let in more of that specific wavelengths or that specific light color. Another possibility is to simply use the stock the stock camera, the stock DSLR. You will still get good results. It's just going to take you a bit more time to get those results. And another possibility is to take a normal DSLR and you can try to mod it yourself or have a shop mod the camera for you, which implies basically removing that little filter on top of the sensor and either just removing it or replacing it with an equivalent piece of glass that is fully transparent. But when you do that, it makes the camera very hard to use for daytime photography in general. You could use a custom balance, or you can use clip-in filters to kind of counteract that it gets a bit complicated. So the easiest is probably to use the stock DSLR or one of those astrophotography specialized DSLRs. But once you've decided upon your DSLR and your lens, or your camera and your lens, you're all good, and we can now go inside the actual tips and tricks on how to get the best use out of your lens. So the first thing that I'm going to touch upon about lenses is the camera lenses are actually they're big pieces of glass. There's tons of glass in there, obviously, and glass can cool down very quickly, more quickly than a lot of other things. And that means that camera lenses, and if you've done nighttime photography, you're probably extremely familiar with that, they're extremely prone to dew, to basically small droplets of water forming on the sensor that can completely kill your astrophotography attempt for the day. And so one of the ways to slow down that dew formation on the lens is to have a lens hood like I have here. And lens hoods, they're normally, like in normal photography, you associate them with avoiding stray light hitting the lens at an angle and causing flares or that kind of stuff. In astrophotography, it has that purpose as well, but it also prevents dew formation. So very often they're actually called dew shields rather than lens hoods. And I have a ton of those for my different lenses because it is quite important to avoid this kind of stuff. There is another tool that I highly recommend to avoid dew formation on the lens, is a band like this, which is basically a resistor that heats up when you put in current through it, and it's called a dew heater, to avoid dew forming on the lens. So with that, the lens is actually kept at a high temperature, or not high temperature, but higher than ambient temperature. The glass itself becomes warm, and so it doesn't cool down, and it makes dew formation, especially with small lenses like that compared to big telescopes, much difficult to happen. So it is very good, although you do need a power source for that. This one is actually 12 volts, but you also have USB dew heaters that I would recommend for nomad or like hiking kind of astrophotography, because then you can use a very small portable battery to use those dew heaters. But especially if you're going to be in a humid climate and you're going to be like above grass or that kind of stuff, dew can really surprise you about how quickly it can come and really ruin your whole night of astrophotography. So this is my first tip. Make sure you have considered dew formation on your lens. This is super important. A second thing with lenses is that they're actually super difficult to bring into focus. And even when you've brought them into focus, if you're using a DSLR, or even if you're using an astrophotography camera and you have the image on your computer, it's very difficult to see whether you have accomplished best focus without taking very long exposures. So it gets really tricky, really difficult, really quickly. And like these focus rings, they're not meant for very precise adjustments. So there's two ways you can do focus. You can use the focus ring manually if your lens supports that, or you can use autofocus, or like to control the focus ring electronically if your lens has that possibility. There are very popular lenses for astrophotography like the Samyang or Rokinon 135mm f2 lens. It's a manual lens, so you're stuck with doing this manually. And there are micro focusers for that basically make that ring move much slower than you can make it with just your hand. I'll put links in the description down below if you're interested. Now, even with those very fine adjustments of the lens ring, whether it is manually with a physical microfocuser or whether you're controlling the lens ring via an adapter like the one that I have here, or via your DSLR that you've connected to a computer or that you are using directly with the manual focus capability, when you have reached best focus, it's actually super hard. Except if you have a tool called a Bahtinov mask. And a Bahtinov mask is something like that. And it's something that you can create yourself. This is a piece of cardboard that I cut in this shape, and it is made so that the stars will have, they're basically will be, I'll put a screenshot so you can see how it looks like, but it's basically a cross like that, and then you have a line in the middle. And if the line is perfectly at the center of the star, it means you have achieved best focus. And this is what is great with those Bahtinov masks. And you can order Bahtinov masks that will be 3D printed, for example. You can make them yourself using cardboard, and there's actually a great Bahtinov mask generator website that you can use. Print out the mask and then cut it out yourself and put it on top of the lens like this. You just, put it on top of the lens, like I do here, and direct at a star, and then you'll be able to achieve great focus. So that's one more tip to use with lenses. Another tip would be if it is able to control the focus link directly with a computer, which is the case for me with my little adapter here, it can actually perform an autofocus routine on the stars that are specialized for star focus, and thus it removes the need for a Bahtinov mask completely. There's one thing more to know about focus for camera lenses, is that due to temperature changes during the night, the lens is actually super sensitive and will change focus throughout the night. So you might have perfect focus at the beginning of the night, but a couple of hours later you check your focus again and you're wildly out of focus. And it happens a lot with camera lenses. So there's a second tip there. You may want to refocus periodically throughout the night. If you're taking exposures on a single subject many times, for a long time, several hours, you may want to manually refocus, stop your capture, stop your intervalometer, whatever, every hour, refocus, and then keep going. So that is something as well to keep in mind. Another thing to be aware of in terms of image quality on star fields for camera lenses is that camera lenses, to connect to a DSLR or to a camera adapter, they use a bayonet type of mount, right? As you know, you can remove it from your DSLR, put it back in, very easy. The problem with those bayonet mounts is that they are actually extremely prone to introducing tilt in your image, meaning that the axis of the light coming through the center of your lens and the focal plane of the sensor, so the actual sensor, are not quite square. They are at a very slight angle. And that angle, even if that angle is off by a fraction of a degree, it can actually have a huge impact on star images, because star images are like that. They're really hard. So I'm putting an image on the screen now, which should be able to see, and basically we have the center of the picture and we have the corners of the pictures, and you'll see that the top right and bottom left corners of that picture, they seem to be completely out of focus, and this is because I have tilt in my sensor. This was taken with a Samyang 135mm f2 lens, and the center is pretty neat, but the corners, as you see, they're very bad, and this is because I have tilt. Now, there are multiple ways you can avoid tilt, and even a few microns can introduce tilts at those very fast focal ratios. You can make tilt more unlikely to happen by having a way of mounting both the camera and the lens and supporting both of them. You can see here I have two rings. One ring supports the camera, the other supports the lens, and that way I can make sure that, you know, the lens is not just like prey to gravity, because gravity will actually change the tilt of your lens. It's your enemy. If you're using a DSLR body directly, so you cannot have a ring for your DSLR, you will likely want to buy a leg for your lens, so that you can support the heavy part, which is the lens. And you may want to kind of try to have some washers or something under your DSLR to make sure that it does not is not a victim of gravity, does not introduce tilt. So I was typically using something like that on the camera lens, and then I had like a screw that I had screwed in through this dovetail that would push against the DSLR body, so that I was sure that they were at the same height and the DSLR body was much less prone to being shifted around relative to the lens by the power of gravity. And really, we're talking about microns here, so you may think like, oh no, mine is super strongly tuned together and it's never going to move. It does, it absolutely does. A few microns is enough. So that's one way to minimize the impact of tilt. Another way, or to basically avoid tilt in the first place, another way to deal with tilt is to actually close down the lens. So this lens is f2.8, but I routinely image with it at f4 for astrophotography. And tilt is one reason. The effects of tilt when you're at f4, that of course the depth of field is smaller then, and so the corners will be less out of focus than what I showed you with the f2 lens earlier. And obviously, the easiest way to reduce the aperture of your lens is to just control the diaphragm inside your lens. My adapter here can do that, and I control it via USB with a computer. And of course, if you're using a DSLR camera body, you can do that via the DSLR camera body. The problem with that is because your diaphragm is not a perfect circle, it has blades, it will introduce diffraction patterns on the star shapes. And I'm putting an example here where you can see the star has tons of little spikes coming out of it. This is due to using the diaphragm within the lens. A much better way of closing down the lens without introducing those star spikes is to use something like this, which are very cheap step-down rings. And step-down rings, they're made officially to basically be able to fit small filters on top of big lenses. But they can be used, they're very effective at just closing down a lens. And I can simply, screw that in. And here we are. It looks pretty weird. It looks like a chameleon eye, right? But with that, we've closed down the lens quite a bit. It's actually roughly at f 4.8, something like that right now. And I can adjust that by, opening up the aperture. And with that, you should keep the diaphragm wide open, so you will not have those diffraction spikes on the stars, and you'll achieve much better looking stars. There's a secondary advantage with that. It's not just the effects of tilt that will be mitigated when you're doing that. There's also the optical aberrations and the optical defects of the lens. So earlier in the video, I was talking about how normal camera lenses, they're not made to photograph starscapes, because starscapes are the most difficult target there is to photograph reliably. And one way and they will have aberrations. And I can give you an example. I'll zoom in on a star that you should be able to see that has star specks as well, but you'll see it has a bit of a little weird little hat that comes out of that star. This is an aberration. This was taken with a Canon 300mm f2.8 lens, stopped down to f3.2, so still stopped down a bit, but there's still this little aberration coming up, and it was much worse wide open. And with those step down rings, you can really close down the lens, and sure, it will make it much slower, but it's still going to be much faster than the refracting telescope that was f4.5 that I showed earlier. So it's something that is a good method to basically achieve better star shapes with your lenses, but at the same time you're nullifying a lot of the advantage of lenses. So they're not faster than refracting telescopes, but at least they'll be smaller and lighter still. And that is really a trick that I highly recommend doing. Closing down your lenses, not using the aperture ring, but using step down rings that are something like $16 or $15 on Amazon. They can be really, really cheap to find. Now, there is something else you can do to kind of fight the optical aberrations of the lens, and this is a pretty involved kind of technique. It's called narrowband imaging. Narrowband imaging with a monochrome camera, it will not work as well, or not at all, with a color camera and dual band filters. But with single band narrowband filters with a monochrome camera, or with a color camera as well, but as long as the filters are single band, they basically isolate a specific wavelength or color of the light, and by doing so they will just like nullify a lot of the optical aberrations that are linked to chromatic aberration, meaning the different wavelengths of light, the different colors are not focused at exactly the same point. So that's another way to do that, but it gets really difficult to do. But I have managed to get excellent pictures at wide open with this lens using narrowband filters, simply because with that most of the optical aberrations of the lens are just neutralized and they're gone, they're not there. It's so much better that way. So that's like a lot of the tips that I have for doing astrophotography with camera lenses. So which is like, be careful of dew, close it down, make sure you can focus properly. If possible, use the focusing motor of the lens when you're closing down the aperture to get better camera image quality and basically lower the effects of tilt of the camera sensor versus the camera lens. You want to use step down rings rather than the internal diaphragm, that kind of stuff. Now there's more things with camera lenses is because of their relatively low focal lengths when you have very portable lenses like this one. So if you're imaging at 135mm at 200mm, or even worse at 50mm like with this lens, you will notice that the star shapes are very blocky, and it's very simple. It's because a single star is covering fewer pixels than if you had zoomed in more. And so what would be a very smooth star, it appears kind of blocky, and there's almost like a black line in between your star and the rest of the background. This can be a bit distracting to some for their pictures. And one of the ways to deal with that is to use a technique called dithering, which is something that Google does automatically in their Pixel smartphones, for example, which is basically moving the camera slightly between exposures. I have a video about that if you're interested, because once you've done dithering, you can use something else, which is called drizzling, which is again something that basically the Google Pixel series does with for their high resolution zoom kind of feature. Pentax cameras use something similar with their micro shift kind of technique. They use a Bayer kind of drizzling, but using a drizzling algorithm, you can fix those star shapes, but it gets more involved. And this leads me to really my first tip and my most important tip with using camera lenses for astrophotography. You should not be what we call a pixel peeper. You should not zoom into your pictures and look at the stars very carefully, because the stars will not have as good of a shape as if you had used a standard refracting telescope. They're going to be a bit more bloated. They'll have maybe a color fringe. They might have a bit of a weird shape. They might have diffraction spikes. Tons of stuff that can happen when using camera lenses, and you'll be much happier if you do not care too much about the star shapes. After you take pictures with a camera lens and you post that picture on an astrophotography forum, people might say like, your star shapes are not good, or that kind of stuff. And I don't care too much about star shapes. And I think that the astrophotography community as a whole focuses a lot on star shapes, and much more than it should. And camera lenses are a way to get decent astrophotography results at a good price with equipment that you might already own, even if it's sacrificing a bit the star shapes and you don't get those perfect pinpoint, super round, beautiful stars that you would with a refracting telescope. So learn to not care too much about that, and you can get excellent results that you'll be absolutely thrilled with using camera lenses rather than buying a refracting telescope. And that's pretty much it for this video. I went through a lot of things about camera lenses, from choosing to actually using them for astrophotography. It's quite complicated. There's so much more to learn about astrophotography. You need to track the stars. You need to do a lot of stuff. I'm not going to go into it into this video, but I hope this was interesting to you. If you like this video and you are new to this channel is mostly about astrophotography, astronomy, typically using more than just camera lenses, but camera lenses is definitely part of my arsenal. If this is something that is interesting to you, feel free to go down below, click that subscribe button, click that little notification bell so that you make sure that you are notified when I get new videos out. And of course, if this video was helpful, or if you have remarks about it, suggestions, or whatever you want, feel free to go down below, click on that like button, and add any comment or suggestions you may add. I read all of the comments and I answer most of them. So with that, thank you so much for watching. Remember, whenever you can, to look up at the stars, and I'll see you next time.